Hello and welcome to this first lecture on PCA. Before we learn how to build a process monitoring solution using PCA, let us understand in detail what is PCA and how to implement it in Python. At a very basic level, PCA is a dimensionality reduction tool. To understand what that means, consider this simple 3D system. Here, it is apparent that even though the original data points lie in this 3D space, most of the data points seem to lie on this 2D plane. And even here, the spread of the data seems to be particularly along one single direction, which is this. What this essentially means is that we can convert this 3D dataset into a 2D dataset or even just a 1D dataset without losing too much information. Let us quickly work this out in Python and see exactly what is entailed. What we want to achieve is this. We will take a simple a 3D system or a 3D dataset and convert that into a 1D dataset using PCA. During this process, we will find the line along which all the data points lie. Let me open up the Jupyter notebook then. Here, you will notice that we have imported some packages already. We have already worked with NumPy and Pandas and Matplotlib before. We have imported this standard scalar from the pre-processing module of sklearn package. This will allow us to scale our data properly. We will see its application later in this script. Another thing that we've imported is this PCA from the decomposition module of the sklearn package. Let us go ahead and see how we can use this. The first thing that we need to do is to read the data provided in this CSV file. So let us read it. For that, we will use pandas to read the data. So we can write our data frame equals. Let us quickly explore how does this data look like. For that, we can just look at the first few rows of this data frame. So we can see we have three variables named X, Y, and Z. And this is how the values look like. Let us plot them so that we can see exactly how these data points are spread in the X, Y, and Z space. As we had previously remarked, the data seems to be spread or lie along a single line. Let us go ahead and fit a PCA model to this. We will convert this data frame into a NumPy array and let us just print out all the values. You could, if you want, just continue with the data frame and use that with the PCA. You don't necessarily have to convert that into a NumPy array. This is how all the 100 samples for X, Y, and Z variables look like. You can see these are raw data. These are not scaled. The first thing that we will do is we will scale them. By scaling them, we mean we will center each column or each variable to be zero mean, and we will normalize them by dividing them by the standard deviation. This we can achieve by using this standard scalar class that we had previously imported into our script. The code for that would simply look like this. We will first create a scalar object from the standard scalar class, and we can now use this object to scale our data. So what has happened, this scalar object has converted each of the three columns of our original data set into a zero mean variable or column with a standard deviation of 1. Now that our data set has been scaled, we are ready to fit a PCA model. This we can do very easily using this PCA class that we had also imported into our script. It is easy and it goes like this. PCA, we will specify that we want just one component and we can fit it After we have fit the PCA model, we can now convert our 3D dataset into this 1D dataset. That is also very easy. We will simply use the PCA object and transform our scaled data to get the data in one dimensional. This score underscore 1D would be a 1D array giving us the transform coordinates in the 1D space for each of the 100 observations. Let us print this out. So this is what your transform data looks like. So you have converted your original array that had 3 variables or 3 columns into a 1D array that has only a single column. So this single column contains all the information that was there in your original array with 3 columns. Therefore, technically, we can recover our original 3D dataset from this 1D dataset. Because remember, I had said that that PCA allows you to convert your data into a lower dimensional space without losing much information. So let us see what does that exactly mean and how we can achieve that. Again, we will use our PCA object to transform this 1D array back into the original space, the X, Y, and Z space. And then we will see how the original dataset and the reconstructed dataset look like. We will again use PCA and use its inverse transform method to convert our score 1D back to the original space. But remember, right now, when PCA will convert it, the reconstructed data would still be in a scaled form. Right? But before we unscale that, let us still print out this reconstructed data. So we can just do print. So this is how your reconstructed data look like. So your original data scaled was here, and your reconstructed data in a scaled form is again here. We will now again transform back this scaled data into an unscaled form so that we can easily compare our original data set, the raw data set, with the reconstructed data set. So data reconstructed equals scalar. Again, we will use the inverse method provided by the scalar object. And what do we scale back? Basically, this reconstructed data in the scaled form. Let us print this out. So this is how our reconstructed data look like. Let us quickly compare. This was our original data. Let us look at the first row. First row was 0, 1.33, and 18.67. In the reconstructed form, it is roughly 0, again roughly 0 and 18.68. Let us also plot both this reconstructed data and the original raw data onto the same plot so that we can easily visualize them. So this is how our data look like. It is even looking here, we can see that our reconstructed data, which is in black dots, are almost along a line. There's a way we can see this 3D plot in a better way by taking this plot out of the Jupyter notebook. So we now obtain a plot like this. In this way, we have the freedom of moving this plot around. By rotating this plot, we can see it more clear what is happening. These brown data points are the original data points, the raw data points, and these black dots are the reconstructed data points. You can see the reconstructed data points seems to be along a single straight line. So what PCA has allowed us to do is to find that single line along which my data points seemed to lie. Okay. For each data point, there's a difference between the raw data and the reconstructed data. We can compute the error between these two data sets. And why do we care about it? Because this, in one way, quantifies the noise in the data samples, which we will then use during the development of our PCA based process monitoring solution. Let us just write this. Let us now create a array or a matrix to store this array in each data sample. So it's simple. This error is between original data and the reconstructed data. Let us print this out. Why? So here we get the error in each dimension or along each variable for each data sample, right? Let us go back to our slideshow now. Now, just like any other machine learning model, PCA also involves a model training step and the model inference or a model deployment step. The task that we performed in the previous Jupyter notebook, where we found the direction of the principal components, that task is called model training. Once your model has been trained, you can apply that model on any test sample to find the transformed coordinates of the test data point in the low dimensional space. Basically, we have our original data point with coordinates x star, y star, and z star, and using our trained PCA model, we have projected it into a low dimensional space where its new coordinates are t1 star and t2 star. So this is t1 star and this is t2 star. And finding these coordinates basically entail projecting this data point onto each of the principal component and then looking at the coordinates along that principal component. PCA seems cool, right? But what specific help does PCA provide in analyzing industrial process data? Well, the rationale is this. Typical modern process plant have hundreds of variables, but they seem to operate in a low dimensional space. Why? Because of constraints imposed by mass balance, thermodynamics, and several enforced product specifications. It all makes it seem like the hundreds of variables, they all seem to be derived from a small number of hidden or unmeasured variables. Therefore, instead of working with hundreds of correlated variables, PCA allows us to work with a handful of uncorrelated variables, which makes their analysis very simple. Moreover, PCA separates the variations that you see in your data into systematic variations and noise. Later on, we will see how we can analyze these systematic variations and the noise separately to build an effective process monitoring tool. Alright, at a conceptual level, we now understand what is PCA. In the next lecture, we will take a peek inside the hood and look at what specific magic is being performed by PCA. See you there then. Bye bye.